A crisp plastic cup presses against the fountain lever. Ice drops with a sharp, rhythmic clink. Dark liquid rushes down, foaming rapidly at the rim as bubbles pop in a frantic, rising chorus. To the person standing there, it is merely a 5-second pit stop, a simple push, a flow of sugar water, and then walking away. But this mundane interaction hides a violent, high-pressure reality. Behind that plastic nozzle lies a complex, mathematically precise chemical battleground. You are not just filling a cup. You are commanding a miniaturized chemical plant operating at breakneck speed. Every millisecond of the pour relies on calibrated engineering that remains invisible to the human eye. While the hand waits for the cup to fill, the internal systems are already engaged in a silent, structural struggle. It is a symphony of fluid dynamics and extreme pressure, working in total isolation to produce the liquid. The machine is a fortress of pipes and valves, a hidden world where chemistry dictates every single drop that hits the ice. This is not just a drink, it is a product of intense, controlled chaos working to deliver a perfect, calculated result. The process begins with the most boring canvas imaginable, plain tap water. It is inert, flat, and unremarkable. To turn this liquid into a weapon of refreshment, the machine initiates a radical transformation. It pulls the water into a pump, driving it forward at a staggering 125 pounds per square inches. That is 3 times the force inside a standard car tire. This is not a gentle flow. It is a violent, high-speed injection. The water is forced directly toward the carbonator, a heavy-duty steel chamber designed to contain the impending volatility. Inside this pressurized vault, the machine performs its primary feat of chemistry. High-pressure CO2 gas is slammed into the chilled stream. There is no room for error. The force of the injection shatters the gas into microscopic bubbles, driving them deep into the water structure. Molecules are trapped, forced to dissolve against their nature, binding together to create carbonic acid. This is the origin of the fizz. The water is no longer just water. It is now a saturated, pressurized solution, vibrating with stored energy. It sits in the chamber, waiting for the final command to release that trapped power. The liquid is ready to bite back. The carbonation is only half the battle. If the water warms, the gas escapes, leaving behind a flat, lifeless liquid. To prevent this, the machine relies on the cold plate. Hidden deep beneath the ice bin, a massive aluminum block acts as a thermal anchor. Lines of water and syrup twist through the metal, winding like veins through a heat sink. The ice above leaches the warmth away, chilling every drop to the very brink of freezing. Only at this near-zero temperature can the liquid hold its volatile, biting fizz. Meanwhile, in the dark back room of the machine, the lifeblood waits. The syrup is thick, viscous, and packed with concentrated flavor. It sits in heavy, sealed boxes, waiting to be moved. The machine initiates the transfer with a series of gas-driven pumps. Fueled by the pressure of the CO2 tank, these pumps begin to cycle. Thump-clack, thump-clack. It is a mechanical heartbeat, steady and relentless. Each stroke bites into the thick sludge, pushing it through the narrow lines toward the dispenser. The sound is rhythmic, a deep internal thudding that marks the movement of the fuel. The system is now fully primed, pressurized, and chilled, holding its breath for the final, violent collision. The customer arrives. A plastic cup presses against the lever, and the circuit closes. Deep inside the dispenser head, 2 solenoid valves snap open with a sharp, metallic click. The wait is over. The pressurized carbonated water and the heavy, syrupy sludge are released from their separate paths. They slam into each other at high velocity. This is the collision point. Inside the nozzle, the geometry is unforgiving. The interior is engineered to force the 2 streams into a violent, high-speed vortex. They swirl, twisting into one another in a precise 5-to-1 ratio. The pressure is immense. The speed is absolute. If the timing of those valves shifts by even a millisecond, or if the ratio drifts by a fraction, the balance fails. A slight misalignment turns the drink into a syrupy, cloying mess or a watery, hollow disappointment. But here, the physics hold. The vortex blends them into a singular, cohesive stream of dark liquid. It pours into the cup, dark and swirling. The foam rises, building a thick, bubbling head at the rim. The machine does not hesitate. It delivers the mixture with calculated, mathematical perfection, holding the ratio steady until the lever is released and the valve slams shut once more. The flow cuts instantly. The last bubbles rise through the dark liquid, popping softly as the foam settles into a thick, tan crown at the rim. You pull the cup away. A single bead of condensation traces a path down the cold plastic, dripping onto the tray. The machine falls silent, the hum of the pumps dying into the ambient noise of the room. You lift the cup. The liquid is still dark and heavy with trapped energy. You take a sip. The carbonation hits, sharp and immediate, followed by the rush of sugar and flavor. A satisfied "ah" escapes. It is a simple moment, but it is not simple at all. You are holding the result of a violent, high-pressure, sub-zero collision. You are tasting the product of a miniaturized chemical plant that measured every drop to a fraction of a percent. From the steel chambers of the carbonator to the rhythmic heartbeat of the syrup lines, you have commanded a symphony of extreme physics. Every time you fill your cup, you are tapping into this hidden, high-speed machinery. It is a calculated, engineered performance designed for one singular purpose: to deliver that perfect, stinging burn in the back of your throat.